CoAP. Protocols are akin to languages, a set of rules to enable devices to communicate. This section deals with CoAP, a protocol designed by an Internet standards body explicitly for applications in IoT. Constrained Application Protocol was designed for machine-to-machine communication in an IoT context. The protocol uses minimum resources and bears similarities to the standard web protocol HTTP. It is agnostic with respect to the payload type. It's designed to cope with millions of links, including to nodes with limited processing capabilities, and it is able to provide strong encryption to combat hacking. Ubiquity. Ubiquity is used here in the sense of being useful anywhere, universally. CoAP achieves ubiquitous connectivity by basing commands on URIs, that is to say, Universal Resource Identifiers, as used by web pages, but in this case prefixed with the word CoAP, by using the REST representational state transfer model, also used in web client-server connections, also by sharing Internet media type definitions with the web, and by using architecture analogous to HTTP, to which it can be easily translated via proxies. Features. At its heart, CoAP provides for an optimization of the existing HTTP protocol. It also adds a built-in means of discovering other participants, multicast support, the ability to define a group of recipients of messages, asynchronous messaging, unlike HTTP, spontaneous interaction without a formal session being needed, and also caching, the ability to store requests and responses, thus saving context to a server. So how is it all put together? This section refers to the Internet Engineering Task Force, IETF, standard RFC 7252. The protocol implements request-response messaging on an asynchronous base. This means that a transport protocol, called UDP, is used to send information. UDP is one of the fundamental Internet protocols, more lightweight than its counterpart TCP, which incorporates more flow control and formal session creation. CoAP allows for the addition of an optional security layer called DTLS. Datagram Transport Layer Security is a method to encrypt UDP packets. Message structure. The first byte is made up as follows. The first two bits of a message define the protocol version, allowing limited scope for future change. Bits 3 to 4 define the type of message confirmation. Possible values are confirmable 0, non-confirmable 1, acknowledgement 2, or reset 3. Thereby, a lack of checks in standard UDP is compensated by a simple method in the CoAP layer itself. A sender can choose whether the message requires a reply, confirmable, or not. The receiver then acknowledges receipt of the confirmable message. Bits 5 to 8 define the token length. A token is a number which matches requests to responses. The token itself is then included in the message directly after the 4-byte header. Byte 2, the message code, is divided into two parts. The first 3 bits define the code. The remaining 5 bits form a subcode. Together, the code and the subcode define what type of request or response is being made. Bytes 3 to 4, the message ID, are used to detect message duplication and to match acknowledgement reset responses to confirmable or non-confirmable messages. In other words, the message ID plays a different role to the token. Whilst the token matches request-response for a given endpoint pair, the message ID keeps track of the delivery of the message. As mentioned above, the token of variable length directly follows the header. There then follows an optional variable length options field. A series of options may be listed, defined in the CoAP Options Numbers Registry. This can include the URI and a string identifier which refers to the Internet media types. The registry has assigned some numeric alternatives to media strings to reduce overhead. Media strings are a more verbose method of specifying the format of the payload. An optional payload field then follows the options field. A single byte with value hexadecimal FF is used to demarcate the end of options and the start of the payload fields. This is where the message content, data, if any, will be transmitted. Message codes. Byte 2 of the CoAP header contains a 3-bit message code class, followed by a 5-bit message code detail, as mentioned in relation to the header. Message codes are denoted by a number, followed by a period, followed by a second number. For example, the range 0.00 to 0.31 are all types of request. For example, 0.01 is a GET message, 0.02 is a POST message, and 0.03 is a PUT message, and so on. Responses have a different message code class. The range for responses is from 2.00 to 5.31. Some examples are 2.01, which means created, 2.02, which indicates deleted, 2.03 stands for valid, and so on. The CoAP standard attempts to cater for all the nuances of types of reply that might be made. For example, 4.00 meaning bad request, 4.01 meaning unauthorized, 4.02 bad option, and so on. Some error numbers may be familiar to web programmers, but the implementation is not identical to the HTTP protocol. Some examples of these are 5.00, a server error, 5.02 indicates bad gateway, 5.04 indicates gateway timeout. Key features. Amongst CoAP's special features are the following: the ability to retransmit when a message gets lost. For example, on a constrained network, the device retransmits at increasingly large intervals, called backing off, until it reaches a definitive timeout. It keeps track of the identifier of the dialog and can perform one such action at a time. That way the network does not become saturated. CoAP also has a built-in potential to communicate machine to machine. Whilst traditional HTTP, on which CoAP is based, functions on a client-server model, carried out within the context of an established session, CoAP adapts the model such that a node may be client and server, enabling connections between simple devices without the need for a central device. Subscriptions. A typical IoT scenario might be where a device is awaiting updates. Device A, wants to know if the state of device B has changed. Repeated requests could flood the network. CoAP has a special way of dealing with this, which is called the Get with Observe option. Core block transfer. IoT protocols are typically concerned with minimizing network transfers, but there may be occasions where bigger transmissions are necessary. For example, where a device needs to upload a firmware update. Block mode allows for this, dividing the large data block into smaller units. For more information, CoAP is developed by the IETF, Internet Engineering Task Force, under reference RFC 7572. The IETF is a global open organization devoted to engineering a smoothly functioning Internet. CoAP